এবং সকল দর্শক এই মুহূর্তে ফেসবুক লাইভ এবং ইউটিউব লাইভের মাধ্যমে আমাদের এই প্রোগ্রামটি দেখছেন, আপনাদের সকলকে আমাদের ফেসবুক পেজ ফিজিক্স আড্ডাতে স্বাগতম। আশা করি সকলে ভালো আছেন এবং সুস্থ আছেন। আমরা দুঃখিত, আসলে বেশ কিছুদিন ধরে আসলে রেগুলারলি প্রোগ্রামটা করতে পারছি না আমার অসুস্থতার কারণে। তো আমরা আবার আজকে আপনাদের মাঝে আসতে পেরেছি নতুন একটা ওয়েবিনার নিয়ে। আজকে আমাদের মাঝে আমাদের যে স্পিকার হিসেবে আছেন তাকে নিয়ে আমরা সবাই গর্ব করি। আজকে আমাদের স্পিকার হিসেবে আমাদের মাঝে উপস্থিত আছেন ডক্টর খন্দকার আব্দুল মুতালিব স্যার। স্যার এখন প্রফেসর হিসেবে কর্মরত আছেন ডিপার্টমেন্ট অফ ফিজিক্স, ইউনিভার্সিটি অফ ফ্লোরিডা। স্যার ফ্লোরিডা ইউএসএ থেকে আমাদের সাথে সংযুক্ত হয়েছেন। স্যার ইতিমধ্যে আমাদের সাথে কানেক্টেড হয়েছেন। তো আমি স্যারকে আমাদের ওয়েবিনারে স্বাগতম জানাচ্ছি। স্যার শুভ সকাল এবং এখানে শুভ সন্ধ্যা সবাইকে। সবাইকে শুভ সন্ধ্যা এবং আপনাকে শুভ সকাল এবং শুভ সন্ধ্যা স্যার, এবং আমাদের ওয়েবিনারে স্বাগতম এবং অনেক অনেক ধন্যবাদ স্যার যে আপনি আপনার ব্যস্ততম সময় থেকে আমাদেরকে সময় দিয়েছেন। তো আশা করি আমাদের ছাত্রছাত্রী এবং দর্শক উপকৃত হবে। আমাদের আসলে এই ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনার আয়োজন করার উদ্দেশ্য, যখন আমরা আয়োজনটা শুরু করলাম প্যান্ডামিকের স্টার্টিং এর সময় থেকে, যখন সবাই ফ্রাস্ট্রেশনে আমরা থাকছিলাম বাসার মধ্যে, এবং ওই সময় আমরা চিন্তা করলাম যে আমাদের সারা বিশ্ব যেহেতু এরকম স্থবির আছে, আমরা অনলাইনের মাধ্যমে আমাদের বড় বড় বিজ্ঞানী যারা বাংলাদেশি বা অন্য দেশের যারা এখন বাসার, তাদেরকে যদি আমরা আমাদের স্টুডেন্টের সাথে কানেক্ট করতে পারি, তাহলে আমরা পরবর্তী জেনারেশন যারা আসলে বিজ্ঞান পড়তে চায়, বিজ্ঞান নিয়ে কাজ করতে চায়, তাদেরকে একটা আসলে প্ল্যাটফর্ম আমরা তৈরি করে দিতে পারি। তারা ঘরে বসে, যেহেতু প্যান্ডামিক তাদেরকে ঘরে থাকতে হচ্ছে, তো ঘরে বসে তারা বিশ্বের মোটামুটি নাম করা বিজ্ঞানীদের সাথে তারা কমিউনিকেট করতে পারবে এবং নতুন নতুন আসলে গবেষণা সম্পর্কে ধারণা পাবে। সেই উদ্দেশ্য নিয়ে স্যার আমাদের যাত্রা, এবং সেই যাত্রাতে স্যার আপনি আমাদেরকে সহযোগিতা করেছেন, তার জন্য আমরা সত্যি কৃতজ্ঞ স্যার। স্যার আপনি স্যার স্ক্রিনটা শেয়ার করতে পারেন এবং আমাদের দর্শক এবং ছাত্রদেরকে বলছি আপনারা চাইলে আমাদের সাথে সংযুক্ত হতে পারেন। আমি লিংক দিব কমেন্ট সেকশনে, এবং আপনারা কমেন্টের মাধ্যমে আমাদের শ্রদ্ধেয় স্যারকে আপনারা আপনাদের প্রশ্ন করতে পারেন।
আমি বোধহয় স্ক্রিনটা অলরেডি শেয়ার করছি। আমি স্ক্রিনটা অলরেডি শেয়ার করছি, তুমি দেখতে পাচ্ছ?
জি স্যার, দেখতে পেয়েছি। আপনি জাস্ট এখন পাওয়ার পয়েন্টে গিয়ে
আমি আগে স্ক্রিনটা বাদ দিয়ে দিই। সো থ্যাংক ইউ সো মাচ। একটু দেরি হয়ে গেল স্টার্ট করতে। আমার ম্যাকটা স্ট্রিম ইয়ার্ডটা একটু নতুন জিনিস, তো আমি জুমে অভ্যস্ত, স্ট্রিম ইয়ার্ড কখনো ব্যবহার করিনি। তো ম্যাকটাকে ঠিক মতো সেট আপ করতে আমার একটু সময় লেগে গেল। আমরা চেষ্টা করছি 10টা থেকে শুরু করেছি, কিন্তু একটু হাফ অ্যান আওয়ার ঠিক করার জন্য, বাট সরি অ্যাবাউট দ্যাট, দেরি হয়ে গেছে। আমি আই আন্ডারস্ট্যান্ড যে এই পাবনা ইউনিভার্সিটি অফ সায়েন্স অ্যান্ড টেকনোলজির একটা রিলেটিভলি ইয়াং ইনস্টিটিউশন, এবং যারা এখন অডিয়েন্সে আছেন তারা আমি শিওর যে জয়েন করছেন বেসিক্যালি বিকজ দে হ্যাভ এ কিউরিয়াস মাইন্ড। আমাদের পৃথিবীর চারিদিকে কি হচ্ছে, ইউনিভার্সে কি হচ্ছে, সে সম্পর্কে কিছু একটা জানার আগ্রহটা। সো ডক্টর দাস এই প্ল্যাটফর্মটাতে বেসিক্যালি সেই আগ্রহটাকেই সাপোর্ট করে যাচ্ছেন, এবং আই এম ভেরি হ্যাপি টু বি পার্ট অফ দ্যাট ওয়ান, টু সাপোর্ট ইট। So let me share. আমি স্ক্রিনটাকে আবার শেয়ার করি। Hopefully it will work this time.
Of course, sir.
Okay.
হ্যাঁ, দেখতে পাচ্ছি।
আচ্ছা, সো আমি তাহলে এইটাকে বাদ দিয়ে
এটাকে মিনিমাইজ করে দেন।
হ্যাঁ, এটাকে মিনিমাইজ করে দিলাম।
আর হাইড, হ্যাঁ জি স্যার, ওটাকে হাইড করে দেন।
এটা আমি view enter full screen. Okay, so title is quantum transport in disordered systems, and when the average is no longer good enough. I have you will notice the second part of the title is in a larger font, written in red color. That means that I'm trying to emphasize this part. So you may not be very interested or understand what quantum transported disordered systems means or what it does. But I'm trying to emphasize is that when we look at nature, most of our descriptions are in terms of the average properties of the nature. But there are situations when that is not only not good enough, but can be very misleading. So what I mean by that one, let me start with a sort of famous product of Pabna. Can you guess what it is? Lychee. Pabna is probably the largest producer in terms of districts in Bangladesh of this particular fruit. Dinajpurke chhadiye geche, as I know. It's called lychee. The British called it lychee, so I had to write it this way. Copied it basically from Wikipedia. But the question that I'm going to ask you is, suppose this is a tree in your backyard and you have this fruit. And I ask you, what is the size of this fruit? How big it is? And you might say that, well, I have eaten it last year and the year before, but I really never measured it exactly, but it should be roughly, what, 1 inch in diameter. So when you say it is roughly 1 inch, there are two elements of uncertainty that you have in your back of your mind. One is that you have never measured it. So it may be 1 inch, which is 25 millimeter, but maybe it's 26 or 24. But there is also another element of randomness in it, the recognition of which is that not all of them are exactly of the same size. So there is some kind of a distribution around some particular value. So if you want to be quantitative, let us say, then what you want to do is take, I don't know, maybe 1,000 of them, measure the diameter of all of them, and then decide what is a good description about the diameter. So if your scale is not going to be very accurate, so what you will do is you will say, okay, all the lychees that have diameter between 25 millimeter plus or minus 0.25 millimeters, we put all of them in one basket. All the lychees that have diameter 26 millimeter plus or minus 0.25 millimeter, we put them in another basket. And then we draw a histogram. Okay. So this is what that histogram might look like. So this big red bar is the number of lychees that had diameter between 25.75 millimeter and 26.25 millimeter within this plus minus 0.25 millimeter range. And there are 770 of them out of 1,000. You will also notice that there are about 100 which has diameter between 25.25 and 25.75, and so on. So this distribution of the diameters has a very sharp peak around a particular value, which is 26 millimeter. If I give you a better scale where instead of plus minus 0.25 millimeter, you can do it as plus minus 0.01 millimeter to that accuracy, then these bars will be much narrower and you'll have many more of those bars. And then you can basically draw a continuous line instead of a histogram. And I have tried to draw that line. This is the blue. I don't know whether you can see it clearly, but it's hidden behind that one. And on the right-hand side, I actually showed the distribution that I fit on the histogram. This is a Gaussian distribution. It's a very well-known mathematical curve that you can plot, symmetric. And you can easily see that if I tell you that the average of the diameter, so I will use this angular bracket to denote an average. So average of this diameter is 26 millimeter, if I tell you that the average diameter is 26 millimeter, it's a fairly good description because most of them have this average, and there's a little plus minus error bar around it, sort of. So if the distribution is very sharp and peaked, then the average is a good description. You might say that, well, I myself have not done this experiment with diameters of lithium, so why I am so confident that the distribution is a Gaussian? Well, it turns out that nature loves Gaussian distribution. So if you, instead of looking at the diameter, if you measure the weight of all these lichens, you see that it has another Gaussian distribution. Completely randomly, if you look at the, let's say, height of all the people in Pabna and plot a distribution like this one, you will get a Gaussian distribution. This is just nature. Of course, there is a reason why nature loves Gaussian distribution. And it's called the law of large numbers. And this is one reason why we understand why average is typically good enough for natural systems. This is known as a Bernoulli trial distribution. You can do this experiment yourself. So you take a coin and you toss it 10 times. Now, each time, the probability of landing a head is 1/2, landing a tail is 1/2. They're equal. For this type of probability system, you can calculate or do a measurement many times and reproduce it. That if I toss a coin just 10 times, then the distribution, the probability of ending up a fraction of times, the head is up. It looks like the top left panel. So you see that the probability that 50% of the time, so fraction 1/2, 0.5, you will end up with head. That probability is the largest, it's about 0.25. But the possibility that you will end up with a head 40% of the time is also not negligible. 30% of the time only, that's also not very negligible. So the fact that this probability has not only 0.5 is a peak, but the width of the distribution is fairly large. So you can only say that, well, the probability of landing a head is 0.5 plus or minus another 0.4 maybe, which does not give you the idea that the average 0.5 is a good description. On the other hand, if you take n equal to 20, so you toss the coin 20 times, then the distribution becomes sharper. Use n equal to 30, even sharper. By the time you go to n equal to 100, see, it's a Gaussian distribution again. With a peak at 0.5, so 50% of the time it will become head, and plus or minus only 0.1. If you go to n equal to 1000, this is going to be even sharper because the width goes down as 1/square root of n. When n is large, the width is very small. So that's the reason, the mathematical reason, why typically we end up with a Gaussian distribution, which is a nice symmetric distribution, and the average, which is the peak value, makes perfect sense. It's a good description of your system. So the question is, I wanted to start the alarm so that, yeah. So the question is, when is the average not a good idea? Okay. So again, let me show the famous Cholon bill in Pabna. I copied it from Banglapedia. So suppose in the dry season, there are some areas where the water is very shallow. Right? So you get this idea that, okay, it's so shallow, I can probably drive across the marshland. And the question is, can you make it? So before you try, of course, for safety reason, you measure the depth of water at many random places. It's going to be different in different places. So you measure the depth at many random places. And you repeat the measurement many, many times, okay? 100 times, maybe 1,000 times, to make sure that you have the right average. And the result is that the average depth is 2 feet. So you say, okay, my car is okay, maybe if I roll up the window, I'll be safe. So I can just drive through. But depending on the average can be downright dangerous. Because although the depth average can be 2 feet, once in a while there will be a big hole that's 10 feet. And you will be in deep trouble. If you knew the distribution, if you actually plotted the distribution of this thing, then it will not be a Gaussian. It will have a long tail. So the average is 2 feet somewhere here. Maybe you can see the cursor. Yeah, so that's the average. But the probability that it has an 8 feet deep hole is not negligible. So a long tail distribution like this one is where average is definitely not a good description, and it can be misleading. Because these rare events in the tail can make a significant difference. So here is the outline of the talk. So I will start with a particular quantity in quantum transport, which is the resistance, or we mostly talk about conductance, which is the inverse of resistance, of just an ordinary electrical wire. And I'll talk about a subtle concept of self-averaging in these macroscopic systems. And then I'll talk about quantum systems where this self-averaging is not present. There, you will have many surprises beyond the average value. Very unusual distributions that you have never seen before. So this is true for a thin quantum wire. If I take a bulk system, then there is even more interesting things because there is a phase transition, quantum phase transition. And to this date, we are so used to looking at average quantities that there is no real theoretical framework that exists to calculate those full distribution of conductances. So if I have time at the end, I'll talk about briefly some novel idea that we are pursuing right now, which is the random matrix theory, based on random matrix theory, and which will give us some idea of what it looks like. Okay, so what do we mean by resistance of a thin wire? Where does it come from? So you take a wire and you connect to the battery. If the resistance is large, then you have a small current flowing through. Small current meaning electrons, small number of them flowing through. If you have a large resistance, then small number of current flowing through. If you have a small resistance, large current. Okay. But if you have a, for example, if your copper wire is perfect, okay, perfect copper wire, crystalline, then the resistance is 0. The electrons just go through. Where do the resistance come from? They come from impurities, defects, many different kinds of imperfections. And we'll basically simplify it and call them all impurities. So there are always these impurities that are randomly placed at different positions. And the electron actually scatters from those random impurities. And it slows down. And that is what leads to resistance. So suppose I have this wire with some resistance, and I have measured it, 20 ohms, but I want to see whether it is the average resistance. So maybe I should take 1,000 of those copies to make sure that the average resistance is 20 ohm. Okay. Now, for the lichus, the reason there were different diameters was the fact of nature that they all come in different sizes. If I repeat this particular wire, where is the element of randomness? The element of randomness is because even if I cut it from the same wire, uniformly disordered. So I have these two different pieces of wire. In the left, I have, let us say, 20 impurities in this unit length. In the right, I have the same length, same size, exactly identical macroscopically, but the impurities, still I have 20 impurities, but they're not sitting at exactly the same positions. Right? They can be randomly placed. Different impurity configurations, what we say. So although they are macroscopically identical, microscopically, the difference is in the configuration of the positions of the impurities. So I take, let's say, I start with 10 of them, just like I had 10 coin tosses, and I expect that there will be big spread of the distribution around some average because I'm only doing 10 objects. But the actual experiment tells you that even with a small number of copies, it gives a very sharp distribution around 20 ohms. So the average is already a very good description. I don't have to go to law of large numbers. And the reason is a little subtle. And if you don't understand the reason behind it, it's perfectly okay. The only thing to remember is that this is a quantum effect. And yeah, let me just explain it a little bit and then see if we understand it. So the electron is a quantum particle. So it has this particle wave duality. So it's both a particle and also acts like a wave. So it has a phase associated with it, which tells you about the quantum nature. Now, when it scatters from these random impurities, it does not lose the phase. It sort of keeps track of the changes in phase perfectly. Once in a while, though, it will encounter a moving atom and scatter from it and lose its energy and lose its phase memory. Once it loses its phase memory, it starts all over again in its journey. So if L phi is a memory length within which the electron has this phase coherence and beyond which it doesn't, then what it means is that you can partition this system into smaller boxes of size L phi, and within each box, it will be a fully quantum object where these different positions of the impurities will make difference. But once you go to the next box, then it has lost all its memory. So the next box is a completely independent copy of the first box. So when you do one measurement, you are actually making n number of measurements of n independent copies, although you have only one macroscopic system. So that's why typically this L phi is very small. So there are 1,000 or even 1,000,000 copies already in your 1-inch wire. So when you do one experiment, you have already satisfied this law of large numbers. So it's a macroscopic measurement already. It's called self-averaging, and that happens whenever your system size is much larger than this memory length. So the question is, how big is the memory length? And here's an experiment that tells you that I have a fixed length, 10 micron by 0.05 micron. And this experiment has been done, silicon MOSFET. The first top curve is at a temperature 1.56 Kelvin. And you see that the difference between different configurations. The gate voltage is a way of changing the configuration. So the different configurations are satisfying this average value. If you lower the temperature 416 millikelvin, it starts to show the difference between different components, members, different configurations. At 107 millikelvin, it is getting crazy. The difference between two neighboring boxes is extremely large. Actually, you don't have two different boxes, because now what has happened is your L5 has become larger than the system size, larger than 10 micron. And therefore, it is only one object, not n different objects. And if you look at only one, then of course, as you change one from the other, the configurations are very different. The conductance is going to be very different. So what we say is that there is no self-averaging at these low temperatures. So that is where you are welcome to the quantum world. You have entered the quantum world at the low temperature, where these fluctuations are important because there is no self-averaging. So let me give you a sort of calculation of quantum transport in thin wires, where I look at a probability distribution of the conductance, just like we look at the distribution of diameters in the for the lichus. I'm going to look at the distribution of conductance, or inverse of resistance, essentially. And conductance is, if the average value of the conductance is much larger than 1 in some units of inverse ohms, then it is weak disorder, meaning that I have only a small number of impurities per unit length. And there, if you actually look at the distribution, it is still Gaussian. For weak disorder, this distribution looks very much Gaussian. There are some interesting caveats about the width, but about universal conductance fluctuation, I'll not talk about that one. But just briefly, it is a Gaussian distribution, and the average for this one will make a good sense. Okay? Makes perfect sense. How about strong disorder, which means where the average of this conductance is much smaller than 1? Just a technical reason I look at log of G rather than G, because G is so small that log G is a bigger number to look at experimentally. So they usually look at expectant value of the average value of log G rather than G. But the only thing that you need to keep in mind is that large G means large gamma. So I define this 1 over gamma as a parameter which describes how strong the disorder is, how many impurities are there per unit length. So if gamma is large, then G is large, which is large conductance, meaning it's a metal. If gamma is very small, then average of G is very small, and that means it is not a metal, it does not like to conduct, we call it an insulator. Okay. So what happens to the distribution of conductance when I have large disorder, meaning gamma is very small? So here is the first plot. This is where gamma is 0.1. So 1 over gamma is 10. So the average of log G, log 1 over G, which is minus log G, is 10. So it is, you can see that, yes, it is a peak of the distribution. So you might say it is an average. That's fine. But it's not a really good average, because it's 10 plus or minus 10. So that does not really tell you that 10 is a good average number. It can be anything in between from 0 to 20. But that's part of the problem. What do you expect at gamma equal to 0.25, for example? Gamma 0.25 means 1 over gamma is 4. So you will expect this peak to happen at 4. This is 5. So you see that you are expecting to see a shift of the peak to the left. What would the shape look like? Well, make your guess. Would the width be smaller, peak larger, something? But definitely you expect a peak at around 4. So here's the result. gamma equal to 0.25. Yes, there is a peak around 4, but it comes down. It's not symmetric anymore. It has a sharp cutoff near 0. Log of G0 means G of the order of 1. Log of 1 is 0. It's no longer a Gaussian. You lower the gamma even further, raise it larger. So gamma equal to 0.25. Next, I'm going to look at gamma equal to 0.4. 1 over gamma is 2.5. Here it is. You still peak at 2.5, okay? That's the average. But it's going to look like very, very asymmetric. Definitely non-Gaussian. The next one is 0.7. So 1 over gamma is 0.143, very close to 0. And it is almost 1/2 of a Gaussian. Remember what a Gaussian looked like? It has become 1/2 of a Gaussian. The other side doesn't exist. If I only told you how the average of G changes from gamma equal to 0.1 to gamma equal to 0.7, would that tell you the whole story? So here is the real experiment. There's a thin wire. It's a strong disorder. There's only one particular disorder, which is close to the gamma equal to 0.7. So look at this plot. It is left-hand side almost missing, right-hand side wide distribution. And this is plotted as minus log G. The experiment plots log of G, so it's negative. So you should flip the other curve. So instead of having cutoff of the left half, here is the cutoff of the right half. Okay, there's nothing on the right side, almost. And then there's a wide distribution on the left-hand side. So that's the real experiment. So we know that this log of G has a very unusual, non-Gaussian, non-symmetric, highly asymmetric distribution. How am I doing in time? Okay. We started late, so I will try to shorten it. So if I, instead of log G, to give us better idea, I plot it P of G versus G. And the metal will be something like a Gaussian. The insulator will be very long tail. And in this crossover that I showed you, the 1/2 of this normal distribution, is a weird animal. Okay, it has a head, it has a tail, it is something like a, it's very weird at this crossover region. And studying only the average G misses all the fun. It's also the misleading. Change your average G and the distribution is completely different. So what is special about 3D? Well, in a bulk, there is a phase transition that occurs at a critical disorder, and that does not happen in thin wires in quasi 1D. So the distribution of conductors in 3D should be more interesting. Let me go through it rather quickly. We don't need to understand all the details, but a phase transition is something where, for example, if you start with a iron material and you start at very high temperature, let's say 2000 degree Kelvin, and then you start lowering the temperature. At some critical temperature, it suddenly becomes a magnet. At a very precise temperature, it suddenly becomes a magnet, ferromagnet. That is known as a critical temperature. So these are classical phase transitions which occurs at a finite temperature, and that's the only thing that we need to know. On the other hand, this metal to insulator transition in 3D that I just mentioned, this is called the Anderson transition. This happens at 0 temperature. And the phase transition is due to some quantum interference effect. Again, if you don't understand it, that's perfectly fine. I'll just briefly tell for those of you who are interested. These random positions of the impurities, oftentimes they sort of complete a loop. And when your electron goes around that loop, it can go clockwise or anti-clockwise. And because it has this quantum nature, it's a wave-like object, those loops can interfere with each other. And the interference pattern gives you a constructive interference because the phase memory is not lost. And then it has a larger probability of staying there and having a localized electron rather than producing a current. And that happens at some particular value of disorder, particular number of impurities per unit length. And that's the phase transition due to quantum interference. But it happens at 0 temperature. So I show you what we understand about this one. You don't have to understand any part of this plot. All it tells is that the theory that you work with is a triumph of quantum field theory, where we can predict that there will be such a phase transition only in 3 dimensions, not in 2 dimensions or 1 dimension. And this is described in terms of this conductance. Remember, this is described in terms of the average conductance. So quantum field theory is a powerful theoretical tool. We have used it very successfully in many different quantum problems. And it was used to predict this nature of this phase transition. And it is experimentally verified. Indeed, there is phase transition only in 3D, not in 2D and 1D. It's a triumph in our understanding of quantum transport. However, it describes this Anderson transition in terms of the average conductance. Even though it occurs when there is no self-averaging, it occurs at 0 temperature. So should we expect something interesting if we look at the distribution? So this is where there is a need for novel ideas. I mean, the standard field theory allows you to calculate the average. It also allows you to calculate the variance, low moments, the width of the distribution, but not the entire weird animal-shaped distribution. That cannot be done. It tries to reconstruct the whole distribution from calculating these moments of the distribution, like average variance, but these moments typically diverge. They become infinity for large disorder, and it cannot be reconstructed. So at the present moment, there is no theoretical framework that exists to study the whole distribution. But we expect the distribution to do very weird things. So can we understand, can we study phase transitions, not in terms of these average quantities, which is the standard practice to do, which is we do it everywhere. All quantum phase transitions are looked at basically in terms of this average value. But it would be a novel thing if we could try to look at the full distribution. And that requires a novel approach. So basically, we have tried one particular approach based on random matrix theory. You don't have to understand anything about it. The whole thing is that if electrons are coming from one end, going out the other end of your system, then this system can be represented by a matrix, a transmission matrix. And because your system is disordered, the elements of this matrix are going to be random with some caveats. So if you look at the eigenvalues of that matrix, you can diagonalize it, look at the eigenvalues, those eigenvalues will also have a random type of distribution. What random matrix theory gives you is a very powerful mathematical tool to study the joint probability distribution of all those eigenvalues, complete distribution. And it turns out, what we showed earlier in 87, that the full P of G, full distribution of conductance, can be calculated directly from this distribution of the eigenvalues that the random matrix theory gives us. So I'll not go into any of the details. It's just that the original random matrix theory that was proposed by Wigner and Dyson in the early 60s, that described the eigenvalues distribution of that one, describes a lot of very disparate things. It describes the distribution in nuclear energy levels, chaotic quantum systems like a quantum dot, even financial correlations, or zeros of Riemann zeta functions, anywhere there are these elements of randomness, this randometrics theory is a very powerful tool to look at the correlations in there. But that's not good enough for a thin wire in our quantum transport problem. So we generalized it in the 90s with some difference that is outlined in this red line. You don't have to understand it. It has become known as Muttalib Borodin ensembles. Very recently, there is a lot of interest in these kind of random matrix ensembles, especially in the mathematics community. But as I told you, that this quasi 1D disordered wire does not give you the phase transition. So we need another generalization with this arrow that gives you this another parameter gamma, and we call it gamma ensembles. We have started looking at it within the last couple of years. And what we have been able to do so far with this gamma ensemble is only look at the average yet, still. But you see, the average as a function of this parameter gamma does show a very rapid drop in 3 dimensions, which is absent in 1 dimension. The average simply smoothly crosses over from metal to insulator in quasi 1D, but it does show this phase transition, at least in terms of the average, in these gamma ensembles. So the next job that we are pursuing right now is to look at the full distribution using this random matrix ensemble like the gamma ensembles. Okay, so the take-home message basically is that the quantum phase transitions like Anderson transition require a novel thinking. We should look at full distributions rather than averages, and all conventional methods fail at this point. So a fascinating possibility is based on this random matrix theory, which, if appropriately generalized, can tell us more about the phase transitions in terms of the distribution rather than in terms of the averages. And perhaps it will lead to new understanding of quantum objects that undergo these kind of phase transitions in disordered systems. Okay, thanks.
Thank you, sir, for a wonderful presentation, sir. So we have got a question.
Yeah.
Okay, so I can add the question in the screen. So, but it is really possible get zero resistance from a pure copper wire?
Yeah. So you never get a pure copper wire. If you build it in the laboratory, by pure I mean it's purely crystalline. Okay. So there's the crystal symmetry. Then there is a powerful mathematical theorem known as the Bloch theorem that tells you that the electrons do not see the atoms at all because they're exactly periodic. And so they propagate without any resistance. So yes, if you can create a pure crystalline copper wire, the resistance will be 0. It will not be a superconductor. That's a different story. It's a perfect conductor, but not a superconductor. But the resistance will be 0. Yes.
Okay, sir. Thank you. So there is no more questions. So as the video will stay remain in YouTube and Facebook. So if we got question, we can communicate with you and we'll let you know about those questions.
Sure.
Thanks again, sir.
Yeah, so sorry about the delay. I may have lost the audience because of the delay.
So I'm also sorry, sir, because due to my health issue, actually, I cannot test before the final program. So due to that, maybe it has happened. So sorry again, sir, and
yeah,
thanks again, sir, for giving us this opportunity.
Sure.
And you have started your lecture with some feature of Pabna, and
yes.
and your delivery very good. You started with fruits and with our beautiful scenery like tunnel bill, and you correlated physics and science with those things. And thanks again, sir, because
Sure.
the main aim of our program is to motivate our students, to encourage them And I think they will definitely encouraged by your exciting lectures, sir. And
Sure.
hopefully
Thank you.
in near future some of our students actually may fall in love in science, and in near future
That's the
they will
goal.
join
Yeah.
in the research field and do something for our mankind, sir. So thanks again,
Thank
sir.
you for providing such a platform that students can get become curious and can get some
Yes, we are
love of
trying,
it.
sir.
Sure. Thank you. Thank you for doing that.
Thank you again, sir. Bye for today, sir.
Bye.
Have a nice day, sir.